Okay, Chapter 9, Asteroids, Comets, and Dwarf Planets. Nature, orbit, and impacts. Let's talk about Chapter 9 and these subjects. Part 1. We'll probably have 2 to 3 parts, but this is the first part. So let's see. Our goals of learning. How do we classify the small bodies? So we have asteroids, and they are rocky in your solar system remnants, and asteroids leave tails in the long exposure images because of the orbital motion around the sun. Now remember, the asteroids are not like comets, and we'll get to that later on in part 1, but just have that in mind that they are not shooting off anything from their surface. The reason that we can see them is because they are moving with respect to the fixed background through a long exposure image. Comets, on the other hand, are icy outer solar system remnants that are remain from the time of the formation of the solar system 4.6 billion years ago. Now, though comets spend most of their time far from the sun, they are best known for their spectacular appearance when they come to the inner part of solar system. When they come to the inner part of solar system, their ices, they're mostly ice and some dust materials. Their ice begin to sublime, so it will leave a formation of a expanding atmosphere, which we call it coma. And but originally they are in a deep freeze in the outer solar system. Once they come into the inner part of solar system, because of the solar radiation, they leave a tail and an atmosphere. But we'll get to that later on as well. Dwarf planets. So dwarf planets are very interesting. In fact, Pluto is one of the dwarf planets. Now, there are small bodies. They are large enough to be round. Remember, if an object wants to be round in spherical shape, it has to be large enough so that the gravity will pull the surrounding material and they collapse on one another layer by layer, and then they eventually become a sphere shape. Now, the discovery of Eris in 2005, it's the second massive dwarf planet in solar system. It's far away from even from Pluto, led to the debate about definition and eventually adoption of the dwarf planet category. So after Neptune, we have a lot of these spherical objects. They're small, smaller than even Moon, but they are big enough to have enough gravity to be round. But then in 2005, we added another category, and we call it dwarf planets. So, meteors and meteorites. So, meteor is a flash of light produced as a small object into the atmosphere. Okay, those lights, those burning flames that you see are called meteor. But the meteorite is an object that survive its trip through the atmosphere and end up on the ground. So if you find a piece of rock, and you're looking at it, it might be an meteorite, and I'm going to show you how you can examine to see if it is a meteorite. But just have in mind that these two are different. One is the flame or the atmosphere or those burning materials. The other one, if it gets to the ground, is just a piece of rock shape that you can find on the ground. Now, our goals of learning for this part. What are asteroids like? Why is there an asteroid belt? And how are meteorites related to asteroids? So, what are the asteroids like? They are, rocky and metallic materials. They're mostly from dust. They're not like comets. Comets are icy materials. They are like dirty snowballs. But in contrast, asteroids are just, rocky materials. And they don't have enough gravity to have a round shape. Well, we call them potato shapes because they usually have these random shapes that look like potatoes. Now, let's talk about facts about them. And we've already covered some of them, but let's go over it one more time. Asteroids are rocky leftovers from planet formations. So since these planets did not form, especially the one that was supposed to be formed between Mars and Jupiter, but it did not, and I'll tell you why in a little bit. So these are the leftovers from the planet formations. The largest one is Ceres, and the diameter is about 1,000 kilometers. That means it's about 30% of the size of the moon. Now, Ceres was discovered, or first captured the image of it by an Italian astronomer in the first day of 19th century, in January 1st, 1801, and it's one of the biggest asteroids that we have. Since then, there are thousands and thousands of, asteroids are known, and there are probably over 1 million of them that have the diameter more than 1 kilometers. But smaller asteroids are just more common than the large asteroids. Large asteroids are very rare, and the reason is that these objects are constantly, impacting one another, colliding with one another, and then eventually, over millions of years, the small asteroids are being more, the numbers of them are more compared to the big asteroids. And the other very important fact about these is that if you add up all the asteroids in the entire solar system, they wouldn't even add up to the smallest terrestrial planets. So if you add them up, they wouldn't even be in the size of Mercury. Okay, that's how small they are. But since they are shattered, and they are, small bodies, and they're all over the place between, 1.8 AU to 4.5 AU. That's essentially between Mars and Jupiter. It looks like a lot, but they are just kilometer-sized objects that are, rotating the sun as well in the stable orbits. Now, when you're looking at some of these asteroids, for example, this one, Matilda, it covered with craters. So these impact parts, these impact areas, shows that this has collided. There's some objects being collided with this asteroid. Now, they have low density, so that means that they're not one solid piece of rock, okay? So there are these probably little collection of these little small particles, or dust grains or gravels just sticking together by a very small gravity. But then it is not a solid one piece of rock. And then these fragments are held together loosely by the gravity. That's why when one of these objects are coming to the inner part of the solar system, or coming to the atmosphere of the Earth, they just being shattered, they're just being broken apart to pieces easily. The reason is that it is not a solid body, and so it will just be broken apart. And when we're looking at some of these asteroids, particularly the ones that are like large, or they're getting close to the Earth, and then potentially be a threat to the life on Earth, they become, our interest to look. So when we're looking at these asteroids, for example, this one, which is probably around 2 kilometers across, we see that it looks like there are 2 asteroids, 2 lobes, 2 nucleus of these asteroids are collided long ago, and then they stick together. So when we want to call it, now, when we're, especially for comets, when we are looking at these 2 lobes, these 2 parts could potentially come from 2 different, formation history. One of them could be rocky, one of them could be metallic. So they could be completely different formation history, but now they're stick together and form one asteroid. And the only reason that we know that it has this shape is because we sent a spacecraft to study this asteroid. Otherwise, we couldn't even tell. Okay? All right. Now, asteroid Vista from DAWN. So DAWN was the mission spacecraft that was sent to the asteroid to study it. So now Vista is much wider across the equator than it is tall. So it looks like something like this. So this area, this diameter is much more compared to this diameter. Okay, this is the equatorial view. When you're looking at it from a south pole of it, or this part of it, you can see that there is a leftover material from an impact that is happened to this asteroid. So as again, they could have a different shapes. Any asteroid is different from another. They are not likely, they're not the same at all. Now, Dawn is currently orbiting Ceres. Ceres is the second asteroid, the second biggest asteroid, so the first big, one of the biggest asteroids in the solar system, as we just talked about it. And when you're looking at this, there are some mysterious things that catch your eye. The first one is these bright spots. What are those? You can see them here. Are they like water from from a frozen water that are shining? Are they salt? Could they be minerals? Could these asteroids come to the Earth when it was still being warm and leave their minerals, and eventually they ended up forming life on Earth? There are also mountains. When you're looking at this, these are big enough. Again, this is probably the 30% size of a moon, so it's big enough that spacecraft can land on. But when you're looking at this, these are mountains in there. But whatever that guess that you have with these bright spots, go to this JPL NASA website and vote for. If you think it's water, vote for water. We don't really know what they are because we don't have a return sample. They're working on it to land on the Ceres, remove some of those materials and bring it back to Earth. In fact, we've done it before for comets, but we have not done it for Ceres yet. There are asteroids that have moons, even though they're small and they don't have enough gravity to to have a spherical shape, but there are, some of them have, especially the large ones, have some moons. There are these little tiny, little small asteroids orbiting the big asteroid. For example, this is asteroid Ida that you can see. And again, this is big enough. If something with this size come to the atmosphere of Earth and then colliding with the Earth, will all be gone for sure. This is the scale is this size is 10 kilometers. So this is probably 40 to 50 kilometers across and probably 20 kilometers wide here, right? So if something like that happened to enter our atmosphere, it will be a huge impact. But then these are, again, large enough that some of these can have their own moon. But how are meteorites related to asteroids? So most meteorites are pieces of asteroids. So when they're coming to the atmosphere, they start to shine and start to heat up, and they are just pieces of asteroids left. Okay. Now let's take a look at some terminologies that we have. So we have meteoroid, a rock from a space that is still orbiting the sun. We have meteorite, a rock from a space that falls through Earth's atmosphere. And then we have meteor, the bright tail left from a meteorite. So this guy, the second one, is actually on the ground now. It survived its trip through the atmosphere, and it is on the ground. Okay. But the shine of it, these flames coming out of it, is called meteor. Okay. But then meteoroid is up here with the D at the end, is just a piece of rock that is still orbiting the sun. Okay, it is still orbiting in the stable orbit around the sun. So we have two different meteorite types. Again, these meteorite types are the ones that are actually underground and survive their trip to the atmosphere to come to Earth. The first one is primitive. They have, as the name suggests, they are unchanged in the composition since they formed 4.6 billion years ago. Okay, so again, these are old enough to be old as the planet formations. They are as old as solar system. And one of the reasons that we know that our solar system is 4.6 billion years is because we have the meteorites. We have these asteroids that are survived their trip to the atmosphere. Now they're underground. We get the sample, we examine the sample, we find out how old it is. Okay. The second one is processed one. They are younger. They have experienced processing, such as volcanoes or differentiations. So these two different types of asteroids, primitives and processed, are the ones that can tell us the history of the solar system. When we're talking about the 4.6 billion years history in our solar system, when we're saying that our solar system formed 4.6 billion years ago, it's because we study these asteroids, these leftovers from planet formations. Okay, if an asteroid in early solar system was big enough to differentiate, if you don't remember what the differentiation is, go back and watch the video of the last two lectures, the last two chapters. We talked about it there very carefully and extensively. So that's why they have an iron core with rocky mantle. So here's an iron core, and then we have a mantle, which is right there, and they are rocky. Now, collision can, and in fact did, break apart at least some asteroids. So these collisions with other asteroids, producing small objects, break apart, the surface, okay? And in fact, these were, a lot that ended up breaking one big spherical asteroid that had a spherical shape to pieces that are not spherical anymore, okay? Now, stony meteorites that are like stone are from rocky mantles. So these spots here that you can see are from these, rocky mantles. In contrast, iron meteorites are from the core that is made of iron. Okay, so if these spots, these little asteroids are colliding with the core, you will end up with the pieces of iron in a meteorite. So when we're talking about asteroids are rocky and form of iron or metal, we're talking about these different two types. All right. In fact, we have different third category, which is called stony iron, and they are formed from a boundary between core and mantle in the asteroid. So in other words, if you're looking at my cursor here, if a piece of asteroid colliding with this area, removing this whole thing, one part of an asteroid will be metallic and one part of it will be rocky. Okay. Why is there an asteroid belt though? Like, we want to know, we have a belt which is called main belt or asteroid belt between Mars and Jupiter. But why is there an asteroid belt there? So that's a picture, okay? That is Earth, and this orange one is Mars. And then we have a huge gap, okay? Jupiter is at 5 AU, or 5 astronomical unit. And then this gap, we have millions of these pieces, okay? Most asteroids orbit in a belt between Mars and Jupiter, around 1.8 to 4.5 AU. So this is essentially between Mars and Jupiter. And then we have Trojan asteroids follow Jupiter's orbit. So this area, which you can see, there are a lot of asteroids there, all right? This area and this area are called Trojan asteroids. These are moving with the same rate as Jupiter, and they are in the Lagrangian points in the solar system, meaning that they will make a 60-degree angle with respect to Sun and with respect to Jupiter. So if you draw a line from this group, in the center of this group to the Sun, and from the center of this group to the Sun, and then if you draw a line from Jupiter to the Sun, they will form equal angles. And then orbit of near-Earth asteroids cross Earth's orbits. So if you're looking at some of these near-Earth objects can cross Earth orbit. And we'll talk about this a little bit more later. Okay, a thought question. Take a look at this. Why are there very few asteroids beyond Jupiter's orbit? Remember have in mind the composition of the asteroids. The composition of asteroids are not icy. It is rock and metal. Okay, now think about this question for a few seconds, and we'll talk about the answer. So A, B, C, or D. My guess is C, because ice could form in the outer solar system. These are metals. The asteroids are forms of metal and rock. They don't have ice. If it had ice on them, it would be considered to be a comet. But since asteroids does not have ice on them, okay, they don't have the water ice, they don't have methane ice, they do not have those. Because of that, um, beyond Jupiter's orbit, it's cold enough. But then since these asteroids are rocky, the answer would be C. Now, another thought question. Which explanation for the asteroid belt seems the most possible? A, B, or C? My answer is C. The belt is where all the asteroids happen to survive. But why didn't they form a planet? So, see, if I am looking at this, that means that I have a let's see. So when we were looking at this, they could have formed a planet, right? All of these objects could stick together, accrete, and eventually form a planet. This is exactly how Jupiter formed. This is exactly how Mars formed, Earth formed, right? But it didn't happen for this belt, and there is a very unique answer to that. The answer is orbital resonance. The orbital resonance is huge. So asteroids in orbital resonance with Jupiter experience periodic notches. Okay, what does that mean? It means that the gravity of Jupiter is big enough that prevent these accretion to happen. They are constantly being disturbed, being notched by the gravity of Jupiter. Eventually, those notches move asteroids out of the resonance orbit, leaving gaps in the belt. So if you're looking at the orbital period in years, and we plot that versus the number of the asteroids, here's where the Earth is. It will take the orbital period of 1 year. Here's Mars, a little bit lower than 2, it's 9.8-ish. And then here's Jupiter, around 12 years. If you're looking so for example, between 3 to 4 years in Earth year, there are a lot of asteroids that are having in that period or in that orbit having this type of period, about 3 to 4 years. But then we have gaps. This gaps is because the orbital period are 1/3 of the orbital period of Jupiter. So here, 4 years is 1/3 of 12. Okay, so that's why there is nothing left here, because it will be captured by Jupiter. Okay, so these notches, because of the gravity and resonance of the Jupiter, is causing these type of leftover materials to not form a bigger planet. So rocky planetesimals between Mars and Jupiter did not accrete into the planet, as we just talked about it. Jupiter's gravity, through influence of orbital resonance, cause these orbits and prevent the accretion to happen. I mean, it could be a planet, small planet, but it didn't happen because this guy is big enough to disturb them. What have you learned? Why is there an asteroid belt? Asteroids are rocky leftovers from the era of the planet formation, so they are old enough as just planets. Orbital resonance with Jupiter prevent rocky planetesimals between Jupiter and Mars to form a planet. And how are meteorites related to asteroids? Most meteorites are just pieces of asteroids, okay? They come to the atmosphere, they burn, we can find them on the ground. And we have two different types, if you remember, primitive and process. Primitive are just safe, they haven't changed, but process one has changed through differentiations. Let's talk about comets, our goals of learning. How do comets get their tail and where do comets come from? So this is Comet Hiakitaki. It was observed in 1997. I remember I was just a small kid looking through the sky. It was bright enough for weeks that you can see in the night sky. I exactly remember this comet in 1997. Now the question is, how do comets get their tail? So let's talk about facts of comets. They form beyond the frost line, which is formed beyond the orbit of Jupiter. And comets are icy compared to asteroids. They have more ice in them compared to asteroids. The nucleus of comets is like, as I said, dirty snowball. It's dust and ice mixed. And most comets do not have tails, okay? I'll talk about how do they end up having a tail eventually. But most comets remain frozen in the outer solar system. Now they have an encounter with one of the giant planets. A passing star goes by. They get gravitationally disturbed from their stable orbit, and they start their journey to the inner part of the solar system. Only comets that enter the inner solar system grow a tail. You cannot expect a piece of ice, to be near Pluto and then having a tail. Once they get closer than 5 AU, once they pass the orbit of Jupiter and encountering more solar radiation, once that happens, they start forming a tail. So nucleus of a comet, we can't really see the nucleus. So this picture is not like if you look at a comet with a telescope, you will see something like this. It's impossible. There, as I said, it's dirty as snowballs. When they come to the inner part of the solar system, their ices begin to sublime. So they leave a freely expanding atmosphere around here, which we call it coma, along with two tails, the dust tail and an ion tail or gas tail. Your book is calling it plasma tail, but I don't think that we call it plasma tail. We call it gas tail or ion tail. Regardless, we have two different tails. Dust tail is just these pieces of dust. This is brighter because they reflect sunlight. And they usually follow the path of, the comet. Not all the times. But again, this gas tail or ion tail is directly in the opposite direction of the sun. So if this area, let me actually show it like that. If this is the way that the gas tail is going, that way I have the sun. So sun is in the opposite direction, okay? Now, let's take a look at this diagram. It will give us a little bit of information. This is not 100% accurate, but it's good enough to understand what's going on. So if the nucleus is really far away, it does not have any kind of activity. Once it's getting past Jupiter, it begins to warm up. And then as it's getting close to the sun, you can see the tails. As I said, not all the comets have tails, especially, for example, Comet Anki, we observed it here in 2017 in St. Louis. It'll come back in 2021 again. Now, Comet Anki is known for a low gas profile. It's not very, you cannot see the gas tail, but it's dusty, so you can see the dust tail. So as they get close, you can see the growth of the gas, which is right here, and you can see the growth of the dust. Now, they will leave some chunks behind, okay? And if Earth passed through those chunks, we'll have a meteor shower at some point, okay? And then as they move away from the sun, they start to cool down again. they do that thousands and thousands and thousands of times until they eventually leave all of their ices, and all the ices are sublimed, and then you'll end up with a rocky or metallic core, which then we call them an asteroid. So a comet can eventually become an asteroid, but an asteroid will never become a comet. Okay. Now, deep impact. Mission to study nucleus of Comet Tempel 1. Its projectile hit the surface in July 4th of July, 2005, and many telescopes to study the aftermath of the impact. I'll show you a little bit of a video at the end of part 1, how the impact happened. So the deep impact, so this is the image of 90 seconds before the impact. And again, this is taken from the camera. And I'll show you the video at the end, as I said. So there are these smooth area, probably about 20 meters high. There are craters. These can show the surface tension at some point. So it could underwent significant, changes. And then we have some rough spots. Again, this is just what we see from a picture. All right. Now, what are comets made out of? So this is a comet. Okay, Tempel 1 was a comet. In fact, it's coming back in 2023, and we're going to study it from here. But what are they made of? They are made of ice. They are made of dust, and they are made of minerals. In fact, one of the hypotheses that we have, that how did we end up having this much water on Earth? Earth formed in a very, very close, distance from the sun, in a warm distance that almost, all the water in the surface was gone. But how did we end up with this amount of water? One of the things that we think that very early on in the history of the solar system, a lot of these comets delivered their ices to Earth. Comets are very fragile. They have a tendency to fall apart just like asteroids. If you're looking at this, the peak brightness is where the nucleus is, but then we have these chunks that are just being broken apart, getting to the small pieces, going to the coma, and your water is vaporized, and the sublimation happens from those chunks as well, leaving some bright spots in a coma. And if I map the intensity of a light, it will probably be something like this. Let me try my best to draw it. So if I map the intensity, okay, let's say this is X and Y. If I map the intensity, the peak intensity will happen at where the nucleus is, and then the intensity will drop, okay? Kind of like that. If you map the intensity, you can see the form of coma. But for this particular comet, these chunks are still bright enough, and you're further away from the nucleus. So if you map the intensity, what would happen is you will have probably something like this. Okay, it means the intensity is high at the nucleus, but it's also high somewhere off nucleus because of these parts, because of these chunks getting broken apart, starting shining, and they look like a comet as well. Okay, so these little parts are still creating the comet. Anyway, that was my poor drawing, but you get the idea. Okay. Stardust mission. Stardust mission went to Comet Wild 2. In fact, in both Wilds, Wild 1 and Wild 2, to return some sample. So these chunks of materials that are coming off nucleus are coming with a very high velocity. And we have a collector, and that collector went to the pod. And then eventually in 2006, the first return sample from a comet got to Earth. Rosetta mission. This has happened very recently. It landed on Comet 67P in 2014 and returned a sample to us. Now, Comet 67P is one of the most famous comets because of its very odd shape. It has two lobes, one up here and one down here, and then there is a neck connecting these two parts. We believe that these two parts are formed in two different formation in the two different area of the solar system. But then because of the disturbance that happened to them, they got stick together with a very slow collision that happened long ago. So when we're looking at these into formation and the composition of these two lobes or these two parts, they are completely different. But since they have collided, we can kind of sample two different formation history in a single comet. The only reason that we know this is because we send a spacecraft to this comet. Otherwise, the coma, the tails, is completely covering the nucleus, so we have no idea what the nucleus looks like. If you want to see the nucleus of Comet Anki, you have to send a spacecraft to it. If you want to see the nucleus of Comet 21P, you have to send a spacecraft to it. If you want to, send to see what the Comet 88P Howell look like, you have to send a spacecraft to it. Otherwise, it is covered and you can't really see. Comets are bigger compared to asteroids. This is Comet 67P versus Los Angeles. If one of these comets come to the atmosphere, I don't know what would happen, but in general, comets are bigger than asteroids, and they have more ice compared to asteroids. And meteors happen when these leftovers debris from comets and asteroids left the comet sitting in this space, and we are seeing them when we pass through them. So in other words, this is us. Comets eject small particles that follow the comet around its orbit and cause meteor showers when Earth crosses the comet's orbits. In other words, it's kind of like that. So let's say that you're driving in a rainy day, right? And then these are the raindrops that are, colliding with your car. But then this is the same exact thing. These are the leftover materials from the debris from the comet's tail, and then we are on a space moving through them, causing these meteor showers to happen on Earth. Okay, now I will show this in a little bit. It's a video showing meteor trailing through Earth's atmosphere. One of the things that I want you to pay attention to is these chunks that are left behind. Once you see the video, you'll see what I'm talking about. This is likely from an asteroid, and okay, I'll show that in a little bit. Where do comets come from? So comets are coming from two different reservoirs, Kuiper Belt and Oort cloud. Kuiper Belt is a belt right here. Let me take a look at my cursor, thank you. So Kuiper Belt is a belt of icy materials, some as small as comets and some big as, dwarf planet Pluto. And they are right after the Neptune, the orbit of Neptune. And they span from 30 AU to 50 AU, okay? If you zoom even further out, you end up to this spherical distribution of, icy materials, which we call it Oort cloud. So this is the Kuiper Belt, and this is the orbit of Neptune, okay? So they're right after the orbit of Neptune, and in fact, Pluto is one of these objects in the Kuiper Belt, okay? But then we have this spherical distribution of icy materials that are going from thousands of AU away from the sun and possibly all the way to the next solar system. So comets coming from Oort cloud are coming from all directions. They don't necessarily lie in the plane of the solar system. But comets from Kuiper Belt are always, coming from, are always, lying in the plane of solar system. So what have you learned? Comets are like dirty snowballs. Most of them are really far from the sun. Once they get close to the sun, they, starting to having tail. Tails grows when comets near the sun, and the nucleus will heat up. Comets in the plane of solar system come from Kuiper Belt. Comets in the random orbits come from Oort cloud, as we just talked about it. So that was the end of part 1, and I'm going to show you the videos that I was speaking about. Okay, let me stop this and share another screen with you. Okay, so you should be able to see this now. Let's play this video. So you can see the asteroid, hitting the atmosphere, and then you can see these flames, these chunks. And then eventually, once it hit the ground and survived, we call it meteorite. So it hit somebody's car. All right, so let me go ahead and stop share and then share another screen with you. Here we go. So this is how to find the asteroids. For example, if I want to see where the asteroids are, how to take an image from an asteroid. If I do that, you can see that this object, this little object, is moving through the sky. Like that object, look. So this is likely an asteroid. These are very long exposure, images. Did you see that? You did not? I'm gonna put some highlight on it. Let's take a look. See this little change right here? Okay. The other thing is the deep impact spacecraft crashing into the Comet Tempel 1. So let's take a look at from the spacecraft. This is how it looks like from the spacecraft. This is when the crash happened. Okay. And view from an impactor. This is the view from impactor. This is the picture that I showed you before. Right. And I'm going to put all of these in the Blackboard as well. So as I said, Pluto is one of the Kuiper Belt objects. It is not one of the planets. And the reason is that it also has a very odd shape of orbit. If you're looking at this, this is Pluto orbit, which is every 248 years doing one complete orbit. And we have Neptune, 164.8 years. But if I move them a little bit, you see what I'm talking about. So their orbit is having a degree of 17 degrees off. So this is the plane of solar system, where the orbit of Neptune is. But see, the Pluto is a little bit off. And this is the one of the Kuiper Belt objects. Okay, we're going to go to part 2 next.